Now we're going to discuss an application of the results of the fact that pressure increases with depth to describe a device called a manometer. And over here I have a schematic diagram of a manometer where it's a device. Say you have a pipe here that has air or water flowing through it, and you want to know what the pressure is inside of that pipe. Well, a U-tube manometer is a very common device for doing so. And essentially how it works is you have what's called a U-tube here. It's shaped like a U, and in that U, you place some sort of heavy fluid. A lot of times it's mercury, at least back in the day it was mercury, or alcohol, or something like that. And the idea is that based on the height based on the rise height of this heavy fluid, you can deduce what the pressure is inside of the tube. Okay, and so now how do we go about doing that? Okay, so how do we find this pressure P inside of the pipe, where we know outside, because again I got the triangle with the three little lines, that's at atmospheric pressure. Well, the answer is we use the result that the pressure is a function only of the depth in the fluid if we are in static equilibrium. And of course there is the caveat is that that's in the same fluid. And now for this we have the added wrinkle that there are multiple fluids, but you'll find out that that's actually not that difficult to use, and there are multiple ways to find P. The first way I'll do it is a bit more cumbersome, but I'll just sort of show it. Okay, so first, when we can use the results of our pressure as a function of depth, that the pressure only increases if we move vertically up and down a leg of the U-tube manometer. If we go horizontally, the pressure does not change, because I proved earlier using a very formal line integral and also just the gradient is that there's no change in pressure if we don't change the elevation. Okay, so we can use that result to realize that that if we start here, go down, and then go back up, you basically realize that you're going down to here. Then from that point you start going down and you go back up, and now you start going back up. And so basically this leg here subtracts out this leg here. So in other words, at any line in the same fluid, the pressure is the same on this green line here on both sides. And you could apply the same argument to here, and what the argument is that you go down and the pressure increases from basically this point here down to here, but then from here you go up the exact same amount and you add and subtract the same rho GH between here, and they basically cancel out, and the pressure winds up being the same. Okay, and now and we can do the same thing. We can apply the exact same logic to this interface, which is right there between the mercury here and the air here. And we could make the argument very easily that the pressure, we'll call it some P1, over here is also the same on both sides, because we are right on the interface between the mercury and the air here. Okay. However, that argument that I just made does not hold if you cross a different fluid. So if I have a line here, I'm going to make that in red, the pressure here is not the same as it is over here. And even though it's the same here as it is over here, it is not the same here as it is over here, because at our line of constant elevation, we have crossed into a different fluid. Okay? And so you can think of that as I'm going to go down and let's say this is mercury here, so that's a super heavy fluid. So I'm going to go down this distance here, then over, then back up in the mercury, and the pressure here is the same. But now when I go back up to this elevation here, I am subtracting out rho gh of the air, but I added a rho gh of the mercury. So as I go back up over here on the air side, I'm not fully subtracting everything out. Okay, so we can basically use these rules to our advantage. Okay, and so now the goal is to use these principles and the pressure variation with depth to find the pressure in this pipe or bulb or whatever it is. Okay, so now let's just find what P1 is here by basically starting in the pipe and walking down to this elevation here because we know they're the same. And we will do this also the same thing on the right. We will start here where we know what the pressure is and walk down to this point here and find and then find P1. And we know that they're supposed to be the same P1. Okay? Yeah, so I'm just going to call the pressure here. Let me get the black. Just call this P1. Okay? So now, first, we are going to assume that rho g is constant in each fluid. So rho g of the mercury is the same and constant on both legs, and rho g of the air or whatever fluid it is constant over here. Okay, and H1, even if it's air, H1 and H2 are usually not that large. And H is the change of elevation between the bulb here and the top of the mercury. And H2 is the distance from the top of the mercury to the bottom of the mercury in the other leg. Okay? And so you can assume that rho g is constant in these because H1 and H2 usually aren't that large. I mean, they're at most, maybe a meter after that. And normally that is a very unpractical manometer to have an H so large. Okay? So if we assume that rho g is H is equal to a constant, well, we can apply so we can do a line integral really from here over to here. Then we can go down and we can find P1. Okay? And the formula for doing so, because we know that this horizontal distance makes no difference in the change of pressure, we only need to consider the vertical distance between here and here. Okay, so we're going to apply our formula from before, where a pressure difference between the starting point and the ending point is just rho g h or depth or whatever it is. Okay, and this d is positive if our final point is lower than our starting point, and this d is negative if our final point is above the starting point. Okay, so let's just apply that rule. So first I will work on this left leg of the manometer. So I have and I'm going to start here and end here. So I have P end, which is P1, minus P start, which is just the pressure that we want, is equal to rho GH of the fluid here. Okay, so that's rho air. I'm just going to call that air times G times this H here, which is H1. Okay, and then we can solve for P. And then P is just, P is just a P1 minus rho air times G times this H over here. And now we do the exact same thing on the right, which is slightly easier because we don't have any horizontal distances to worry about. Okay, so I'm going to start here and go down to here. So I'm going to start with P naught, and I'm going to go down H2 and multiply that by rho G of the mercury, which is exactly what I did here. Okay, so I can solve this for P1. So I'm going to end at P1, and I started at where we knew the pressure to be atmospheric, and I solve for P1. Okay, and now I can take that P1 and then stuff it into our expression for P. And you basically do that, and you can eliminate P1. And when you do so, we get that the pressure in the pipe is equal to the atmospheric pressure plus a rho g times g times H2 minus the density of the air times g times H1. So basically, all's P is, all that pressure is the atmospheric pressure plus the change of pressure in the mercury due to this depth, and we subtract out, because we're going up again, the pressure in the fluid on the left. Okay, that's basically all that formula says. Okay. Okay, and so that's just, I showed you how to solve a simple manometer problem by way of example. And now there is another way to do this, and we can really use, and if we really think about this, I know it's kind of awful to think that this is a more natural way to think about this, but let's say we have another goofy manometer. Well, really what we did here is I started here and walked to this point here, and I started here and walked to this point here, and used the fact that the sort of pressure is the same between those 2 points. But to me, a more natural way to think about this is actually to think about how you would do this with a line integral. Because in the fluid inside of this tube, the line integral is valid, because in this tube, grad P equals rho g, and that is dependent, and then that works everywhere. It does not matter what fluid you are in, whether you're in the air or you're in the mercury, that always works. And you can still use a line integral, and you just pick a starting point, and you walk down the tube until you until you get to your ending point. And that is another way of doing it. And to me, that's a more natural way of doing it. Okay? So, that said, we can find pressure on basically one end by starting at the other end and basically adding up all the delta P's in each fluid. And basically, what I'm saying here is that we use a line we do a line integral here, and basically start on one side and walk in the tube all the way to the other side. And note, we cannot go through the tube like that. That is an invalid path, because we cross the tube wall. And the static equilibrium condition for a fluid does not hold across the tube wall, because that's solid, and there may be a perfect vacuum out here if it's in outer space. And so grad P equals rho g is definitely, it may or may not be valid out here too. Okay? So now, but in the end, you can think of, well, this is a really nasty line integral, I don't want to do that. Well, it turns out you don't have to do a difficult line integral for a nasty function in a crazy path, because we know that only the vertical distances add anything to the line integral. So basically what you can think of is that you're going to pick a starting point, and we're going to start here and say go down to here, and we're going to add, and we have the starting pressure, and we're going to add a delta P for basically this section here. Then we're going to add a delta P for this section here, actually subtract, and then we're going to subtract another delta P in this section here. So basically, as long as you have nice, clearly defined sections, you can just basically add all the delta P's across each little section to the starting pressure. Okay, and so basically we sort of walk around the manometer and add all the delta P for each fluid we encounter. Okay. And we basically just add up all the delta P's, and we just basically add delta P's for each fluid, and it's a sum over an arbitrary number of fluids, and we just count the fluid in the order that we encounter them. Okay, and I'll show you by way of example in a few minutes. Okay, and so we can define delta Pi is just rho I times G HI. Okay, then, and of course this is only valid if all the rho i's are constant and G is also constant. If not, you would have to basically do the formal integral if this was not constant. If this was invalid, this is just a little aside, we'd have delta Pi equals the integral from 0 to some depth, rho G dy. Okay. Oops, sorry about that. I hit a button. And so that is, and so that's what you could do if you had a manometer on Jupiter or something like that. I don't know why you would do that, but you know, you never know. Okay, and so we can basically, by basically adding all the delta P's, we know that P equals P start to the pressure at our starting point, plus G, that's the same for all fluids, times the density of that fluid, times the change of height of that fluid. Okay, and basically sometimes you know the change of height of the fluid here, like you do here, or sometimes it's more convenient to draw a datum, and you know the specific heights of the starting and the starting and the ending points. So you can also think of this as just the elevation, a difference between the starting and the ending points. Okay, and if you substitute that in, you get this formula here, where P is equal to P start plus G times rho I times the change of height. And either of these two formulas are valid. It just depends on how, for a given scenario, which is more convenient to express your elevation differences in. Okay. Okay, and so I'm going to apply this to the manometer, and sometimes it's again helpful to add a datum plane below. And so I'm going to apply this to the exact same manometer here. I'm going to start at this point here because I know what the pressure is, and I'm just going to walk around until I get to my ending point. Okay, so I'm going to start on the P naught side, and so P start is just the atmospheric pressure P naught. Okay, and then I'm going to begin walking, and then I'm just going to, then when I begin walking, I encounter the first fluid, which is the mercury. Okay. And then with that, and then I just keep tabs on what the density is of that. That's just the density of mercury, and what H start is. And now, so now I got all the information of the fluid and the starting point, and now I'm going to walk down until I get to the end. Okay, or I'm going to keep walking in that fluid and around and back up until I encounter a new fluid, which is at this interface right here, because it's air here and mercury here. Okay, so I keep walking until I encounter a new fluid, and that elevation, which you keep track of, will be H and 1. And so for this case, H and 1 is equal to H2. I'm going to scroll back up. And so H2 is right here. This is where the interface is, and so I'm going to walk around. I'm starting here at H1. I go down, and then I go back up, and I wind back up at this height here, H2. Okay. Then after that I encounter the air. So rho 2 is equal to the density of the air, and H start 2 is equal to Hn1. Basically, we are starting in the air where we ended in the mercury, and that's H2. And now I walk in the air until we reach the end, and so so the end of our second fluid is the elevation at the end of our second fluid is H3. So I'm going to scroll back up, and so H3 is just this distance here. Okay, so now we know all the fluids and the elevations, and so we can just apply the formula that P is equal to P start plus the sum of all the densities in our different regions times the change in the elevation for each fluid. Okay, and that's equal to a P start. And I got two fluids here. I got rho 1 times G times H start 1 minus H end 1 plus rho 2 times G times H start 2 minus H end 2. Okay, and so P start is P naught. Rho 1 is the density of mercury. This is H1. This is H2. Rho 2 is rho air. The starting point for the air is H2, and the ending point is H3. Okay, and so we apply the formula, stick everything in. Well, oops, this here is just small h2 that we had in the diagram. This here is just minus h1 that we had in the diagram. And we apply the formula, and we get that P is equal to P naught plus G times the density of mercury times H2, a small h2 minus rho air times small h1, which is identical to the result that we had before. And the other way that you could think about this, instead of drawing a datum, we could just directly use H2 and small h1, and you can do that. Alternative. If you know the change of height, you can just basically sum those up directly, and just know that delta H is positive if you're going down in your path, and it's negative if you are going up. Okay. So basically, it is greater than 0 if the path is down, which is in the direction of gravity, and it's less than 0 if the path is up, which means the opposite of gravity. Okay? So example for this little manometer here, if we start at PA here, and we want to end up at PB, well, we have gone, in this fluid here, we have gone up a delta H, so we subtract off a rho G delta H from PA. And if we start at PB, we basically add it because we basically went down. Okay. So this procedure, I think, is a bit more straightforward. It doesn't look like it, but it really is. It works for an arbitrary number of fluids, and you may have more than one fluid. For example, you could easily have a case where you have a manometer and there's an air bubble trapped in it, which you really don't want because it will not give you an accurate reading. Okay, and so that's really about all there is to the theory of manometers. Now I'm just going to go over an example. And so our example is we have sort of a crazy manometer. Okay, and that crazy manometer is here. It has a fuel oil line here, and we have a pressure tap or a hole drilled into the side of it, and we're going to measure the pressure in the pipe using a manometer, and this manometer happens to have, including the fuel oil, it happens to have 4 different fluids. I don't know why on earth you would want a manometer like that, but that's the way it is. So we have fuel over here, and we have the specific weight of 53 pounds-force per cubic foot. Then we have the mercury, which is right here, which has a specific weight of 847 pounds-force per cubic foot. Then these blue pieces here are SAE30 oil, and that has a specific weight of 57 pounds-force per cubic foot. And between these sections of SAE30 oil, we have an air bubble trapped. And we know that the pressure here is 15.3 pounds-force per square inch. And we're asked to find what is the pressure at point B. Okay, and so I know all the changes of the elevation. I know basically this height here, which is related to this height here. I know this height here. I know this height here, and I know this height here, and I know this height here. Okay, and so I know all the specific weights, I know all the elevations, and I know all the fluids. So really, so this is what we're given. So now I want to find PB. So really, and we're going to, and so basically really, you just start at A and walk around until you hit B, doing the line integral procedure, which of course is just that formula that it has the sums in it. So we're going to assume that rho g is constant for each fluid. Typically, I would have an assumption section, and you would say that rho equals constant, and g equals constant. Okay, and so we can only use the formula that that I'm going to use here because we're assuming that rho is constant and g is constant for each fluid. Okay. Okay, so in your homework, I want you to write all these assumptions down because basically this tells me that you actually understand what you're doing as opposed to just grabbing formulas from the book. And this also basically stating these two things here means that you have and also we're implicitly assuming static equilibrium. So if we assume static equilibrium, constant density, and constant gravity, we can use the nice formulas that that we deduced above. So we can assume, so based on that assumption, we can use this equation here where the pressure at the end is equal to the starting pressure plus the sum of rho I for all the fluids times G times delta HI. Well, recall that that rho times G is just the specific weight of the fluid. And when I do that, you can substitute that in, and then Pn is equal to P start plus the sum of the specific weight times the change of height for each fluid. And in this case, the change of height version is actually a little bit easier to use than the data method, but you could use either or. Your call. Okay. And so we're going to start at A, which is over here, and we're going to walk towards B, and we're just going to count up the number of different sections that contain different fluids. And so by doing that, I have the fuel oil here. That is section 1. I have the mercury here. That is section 2. I have SAE30 oil here. That is section 3. I have air here. That is section 4. And I have a second section of SAE30 oil, and I'm going to call that section 5. Even though they have the exact same fluid, I'm going to call those different sections because they're not connected. Okay, so I'm just gonna do that. And so we have for fluid 1, which is the fuel oil, we just basically write down what we know about fluid 1. We know that gamma 1 is 53 pounds force per cubic foot. And now we just start keeping tabs on the change of elevation for that. Okay, and so I'm going to scroll back up to show the diagram. So we know that the distance between here and here is 18 inches, and the distance between here and here is 3 inches. So the total height for fluid 1 is just basically this height here. And we are starting from here and moving down in our path. So that delta H is positive because we are going down into the, because we are going in the direction of gravity. Okay? And so that's where I get this 3 inches here and this 18 inches here. And we get the total change of elevation for the first fluid is 21 inches. And we can do that because the interface between, because we basically went down to reach the next fluid. Okay, so now we are in fluid 2, which is the mercury. And we just basically keep books. We know the specific weight. I've given that. That's 847 pounds force per foot cubed. And I know the change of elevation. I'm going to scroll back up. The change of elevation here is I'm going to start here, go back down 6 inches. Then I'm going to go down 7 inches, over, then up 7 inches. Again, so basically these 7 inches here cancels out with the 7 inches over there. So on net, I've gone down 6 inches. Okay. So on net, I've gone down 6 inches, and it's positive. It's positive because the next interface is lower, that I've gone down 6 inches. So after that, I've hit fluid 3. Fluid 3 is the SAE30 oil. Okay, and I just write down gamma for that, or density if you know density. And then for that fluid, I go up 6 inches, and then I go up another 18 inches until I hit the air interface. Okay. So I just keep tabs of that. And so the change of height here is 18 plus 6 inches. And that implies that delta H3 is negative 24 inches. Okay? And the reason it is negative 24 inches is because we have that the next interface was actually higher. And because it's higher, we are subtracting pressure off because we are going against the gravity. Okay? And now we are now in fluid floor. Fluid floor is the air bubble. And so gamma 4 is just gamma for the air. And it turns out that delta H4 is 0. And the reason that it's 0 is because we start over here, we go up 3 inches, over, then down 3 inches. Okay? And then also you could neglect this because typically gamma of air is much, much smaller than gamma of a liquid. Okay, for instance, the specific weight of air is at atmospheric pressure is about 1,000 times less than what it is for a liquid. So unless we went up in the air on the order of like a half mile, that's going to have absolutely no change of pressure relative to this liquid here. Okay, so in most cases, if you have an air bubble, you can neglect the pressure across that if you're not given a specific weight or a density, just because it's so low. Okay, then after the air bubble, we hit fluid 5, And fluid 5 is another section with the SA30 oil that got split into two pieces by the air bubble. And so gamma 5 is just the same 57 pounds-force per cubic foot, just like it was for the third segment, our third fluid, I should say. And here we've gone down 5 inches. And because we've gone down 5 inches, it's a positive number. Okay. So then we know all the pieces. We know all five segments. We know all the gammas, and we know all the change of heights. So now we just literally stuff it in. Okay. So then P end, equals P start plus the sum of gamma I hi. And I just do that sum. So PB is equal to PA plus gamma 1 H1 plus gamma 2 H2, gamma 3 delta H3, gamma 4 delta H4, gamma 5 delta H5. And then I just stuff in the numbers. And I have PA here, and I have all the numbers here. And note that I am explicitly putting all the units attached to every single number. And that is, and in your homework, I demand that you do that, especially with the English system, to avoid making mistakes. And I have a conversion factor, which I show right here, where I convert cubic feet to inches. Okay. And so I can punch the numbers into the calculator, and I wind up that PB is 18.13 pounds-force per inch squared. Okay, and so that's basically how you do it. So after you get the hang of it, these are actually pretty straightforward problems. You just have to do it a few times. So I recommend you look at the sample problems, try to do them on your own, as they will be really helpful to you. Okay, now there's a pretty common wrinkle that occurs with a manometer, and that's what if there's a change in the cross-sectional area? Okay, and that could be, you have a manometer here, okay, and you have a tube here, and it has a bigger diameter here than it has over here, and there's a specific reason that's done. Okay, and so we're going to assume it's a tube. And now, even though this tube area here is bigger than this tube area here, the hydrostatic equilibrium condition still applies. The fact that this tube here, that it's bigger diameter than it is over here, that has no bearing on the change of height at the static equilibrium condition. So we know that PA equals PB over here plus this little section here. I keep bumping it. Sorry about that. And so I'm just going to call this fluid mercury for the sake of argument here, and it's just PB plus rho GH, rho GH1 here. Okay. And of course, we're going to assume that PA is higher than is basically higher than PB, which means that H1 will that the height of the mercury here will be higher than it is over here. Now, what normally happens if you have a flow device in a plant is you will typically calibrate a manometer to a specific pressure. Then you will basically monitor the change in the elevation due to a change of the pressure in A. Okay, so that basically means what if PA is changed to some new pressure? How far down does the mercury on the left side here go down, or how much does the mercury on basically this side here go up? Okay, and so if we assume that PA is basically increased, that means that means the height of the mercury here is going to go up, and this change of height here between the level of the mercury here and the level of the mercury here is going to go up. Okay, so and also we know that kind of intuitively that if there is higher pressure here, that means that the higher pressure is actually gonna push more of the mercury down. Okay, and it's gonna push it down into this little tube, and it's gonna go up, and it's gonna move up on the other side. So if I draw a little diagram here of that case, so now these dashed lines here are the original heights. Now I've taken that basically stable operating pressure and I've bumped the pressure up a bit. And now I'm asking what's going to happen to the interfaces to the mercury interface here and the mercury interface there if I bump up the pressure. Well, I know that this distance here, that it's going to be displaced, that the mercury interface here is going to be displaced downwards by some distance delta 1. And I know that on the other two, because the mercury that's being displaced down here, it has to go somewhere, and it's going to be pushed into the tube on the right, and it's going to cause the mercury interface over here to go up. Okay, by some distance delta 2. So now let's apply static equilibrium to this configuration, and we find that PA of the change pressure is equal to PB plus rho g times the total height between this height and this height here. Well, this distance here is delta H2 plus H1 plus delta 1. So we got to add all three of these pieces. But unfortunately, we don't know what delta 2 is, and we don't know what delta 1 is. And so we need a way to eliminate a delta 1 and or delta 2. So how do we do that? Okay. And so basically what do we use? Well, in reality, I kind of said it. We use essentially conservation of mass. Basically, we note that the volume of fluid here, the volume of liquid rather, all the volume here, it's being pushed out of this big section here and being pushed into this little section here. And so what that means is that the liquid volume that is lost on this side here, it must be added to this side here. And now, note in general, you can apply conservation of mass, but it turns out that the volumetric flow rate of a liquid is essentially preserved and is also conserved. And we will discuss that much more in detail later on in class. Okay, but for the time being now, you just need to understand that it's the change of volume that we are after. Okay? And that's just due to the fact that you can't really compress a liquid. Okay? Or a liquid is called an incompressible fluid. And we will discuss that in much more detail later on. So now we just keep track. Now, to relate delta 1, the change of height in 1 to the change of height of 2, what we will do is just keep track of the mass or of the volume lost on the left and the volume gained on the right. Okay, which is just really simple geometry. So the change of volume on the left is just the cross-sectional area of the tube over here times the height. Oops, and I got G here for some reason. Okay, and then that's just the cross-sectional area. That's pi over 4 d1 squared. And this is the amount that the Hg moved down on this side because we've bumped the pressure here up. Okay, and so now that is this little, that's the volume of this green shaded region here. Now, I need to equate that to the volume of the green shaded region on the right. So I'm going to do that, and the liquid volume gain on the right is simply A2, which is the cross-sectional area of the tube over here, times the change of height of 2, because basically the fluid interface is moved up. And so that again is just the cross-sectional area is just pi d squared, and delta 2 is just the amount that the mercury has has basically risen on the right side. And we know that the change of volume here must be the same as is over here, so we basically equate these two. Okay? And so we know that the change of volume on the left side is equal to the change of volume on the right side, and we equate them. And I got these G's here. I was using mass before, but it's actually more correct to use volume. Sorry about that. So I know that area times the change of height on the left is equal to the area times the change of height on the right. I substitute in what we know, and I know that basically delta 2 is, or the rise of the fluid on the right side is equal to this expression here, just the ratio of the cross-sectional areas times delta 1. I substitute in the pi d squareds, and I do some simplification, and I wind up with that delta 2 is just equal to delta 1 times d squared. Okay, so I now know delta 2 in relation to delta 1. So I know that PA2 is equal to PB plus rho hg times g times the total height difference at the higher pressure, which is delta 2 plus h1 plus delta 1. Okay, and I can substitute in our expression here for delta 2, and which is delta 1 d1 squared over 2. So I have PB rho hg times g times delta 1 times d squared times d1 over d2, and that whole quantity squared, plus h1 times delta 1. Or I can solve for delta 1, and I got this, and I can simplify, and we can solve for delta 1 in terms of the pressure difference times the weight of the mercury times the diameters times d2 squared. And so really why we do this is in many scenarios what this turns in many scenarios, we want to make a very sensitive gauge that can detect a change of pressure. So for instance, if you're in a plant and you're monitoring, I don't know, a water pressure in a pipe, you don't necessarily care what the absolute pressure is, but you want to know if there's a pressure excursion. And so you want a nice gauge that can just tell you how much the pressure has changed. And so essentially then what they'll do, or what they did back in the day, is they would use a manometer like this, and to make it very sensitive so that you can very easily see if there's a change of pressure, is they would make the cross-sectional area here large and the cross-sectional area here small. And then basically in the window of the manometer, it would basically record this height here, and then they'd basically correlate the change of pressure to, or they'd calibrate it so that you'd know the change of pressure just based on this one height here. So you could just look at it, get a reading, and get a nice measurement. Now, if the cross-sectional areas were the same, this change of height here, according to the formula here that I learned, this change of height here is actually going to be quite a bit smaller. And so what that means is that your measurement's not going to be as sensitive. So if there's a small change of pressure, the basically rise height on the right side is actually going to be very small, and you're not going to be able to really see anything. And so engineers will play games like this to try to make a nice, very sensitive measurement. Okay, and so in many scenarios, we want delta 2 divided by delta 1 to be as large as practical. And this will increase the sensitivity of your measurement, which makes it a lot easier to read. Okay, and notice here, notice here I didn't stick in any numbers. So in your homework, I want you to work symbolically when practical until the very end. Now, for the manometer problem that I did previously, it's not practical to do that. Okay, but for problems like this, you really need to get into the habit of using symbolic forms, or a symbolic form until the very end. The reason being is, like, some problems will ask you to evaluate this expression, with about 4 or 5 different combinations of parameters, just so you can get a feel for the effect of a change of variable. Okay, now if you had to go through this entire procedure up here, procedure every single time, it would take you forever to complete the problem. But if you go and derive a nice analytical formula like this, you can just stuff them in. And it actually saves you time in the long run. And you can look at the behavior, and you can look at the formula and see what happens, just based on the parameters. Okay? And so, because basically we basically learned that the change of height of 2 is proportional to the cross-sectional area of the larger section squared. We basically learned that, and that is a nice simple result, and it's multiplied by a more complex bogey factor over here. But basically by working through this, we learn a lot about our system. Okay, and so